Matrices are the foundations of linear algebra. Even vectors that we dealt with in the previous video are special matrices. They are column matrices. So we have to understand matrices and how they interact with each other at a very deep level. At the core of it, a matrix is just a table of numbers. It's a two-dimensional array. So it's got a number of rows and number of columns, and usually written like an m by n matrix. So read it as m by n. Not m times n, m by n. So a 3 by 4 matrix will have 3 rows and 4 columns. Rows first and columns second. So there it is, a 3 by 4 matrix. So we will write this as A is a member of R, our friend, 3 by 4. 3 by 4 saying that there is a set of all possible matrices of size 3 by 4 with real elements. And that set is called R3 by 4, and A is of course a member of that. And that's the way we'll write it. So it's set notation as usual. Then parallel to what we did in vectors, there's a scalar multiplication and an addition. Scalar multiplication is just scaling each element by the scalar that you specify, which is expected to be in the same field as the numbers of the matrix belong to. 3 times 1, 3 times 3, 3 times 2, 3 times 1. Very simple. If you have two matrices of the same size, then you can add them element by element addition. Very easy to understand that also. Identical to actually what we did in vectors, which is not surprising because vectors are indeed matrices of special shapes. So vectors are columns of numbers. They are just column matrices. It's the same as a matrix of size n by 1. But you wouldn't write that as Rn by 1, you'll just say Rn. So we use small letters in our book to represent vectors, but bolded. Unbolded small letters are just real numbers. So as you saw, matrices and vectors obey the same rules of scalar multiplication and addition and multiplication, which we haven't defined yet. Then the last thing, even though our vectors are all column vectors, there are people that think of rows of numbers as a row vector, but that's not that common. We, in this course, will stay away from such abominations as row vectors. So as you can imagine, even though we started with vectors being special matrices, we needn't have studied vectors separately and defined their operations. Those things are subsumed by the corresponding operations and treatment of matrices. One thing to keep in mind is that there is a conformance requirement for addition for matrices. So matrices of different sizes cannot add. So as a special case, vectors of different sizes cannot add and vectors cannot add to matrices, etc. One important concept is that the zero vector in R3 is not the same as the zero vector in R2. Some of my students do get misguided by this because they think of R3 as a three-dimensional space. And then they think that R2 is just one plane, like let's say the XY plane of R3. Inside R3, there is an R2. And then they think of the zero vector in R3 the same as the zero vector in that plane. That's not the way to think of it at all in this course. There is an R3 somewhere, but R2 has got nothing to do with that picture. It's a completely separate universe. So it's a two-dimensional universe somewhere else. There are vectors there. Those vectors don't interact directly with the vectors in R3. One more thing to actually kind of notice is a similarity between the conditions of linearity, homogeneity and additivity, and the definitions of scalar multiplication and vector addition or the matrix addition. Those things are not accidents. Those are by design. Those operations and those definitions, those conditions of linearity, those are the foundations of linear algebra. Now, some formal properties of scalar multiplication and addition. This time we're talking about it from the perspective of matrices and vectors. So the order doesn't matter in scaling, whether it is a vector, which is a special case of matrix. So order doesn't matter. Addition also, order doesn't matter. x1 plus x2 is x2 plus x1 because the underlying operations are basically just real numbers adding or multiplying. A plus b as matrices is the same as b plus a. They are associative also for the same reason. The underlying operations are just additions and multiplications in real numbers. So you can group them in any fashion that you want. That is fine. So addition also is associative. So is scalar multiplication, matrix addition, etc. And you can distribute and pull out factors And that also is from the fact that the underlying operations are merely operations on real numbers. Now the next topic is going to be a big one. It is matrix multiplication. So that will be the next video.